Okay, so last time we derived the weak form of our weighted average residual equation. So let's write that down again, because it's going to be our starting point for this time. It was the integral over the area of F times rho C d temperature d time plus the integral over the area of K, and we had df dx dt dx plus df dy dt dy dA minus the integral over the area of f g triple prime dA equals the integral over the boundary of f times the heat flux normal to the boundary ds. And what made the weak form different from the strong form was that this term and this term used to be something maybe a little more familiar, which was the integral over the area of f times d dx of minus k dt dx plus d dy of minus k dt dy, like that. So basically what we did last time was, through integration by parts, we turned this sort of familiar looking thing into this and this, which are maybe a little bit less familiar. So what we need to do now is come up with a form for f, which is our weighting function, and we'll see that there's actually a number of weighting functions that we'll use, and a form for t, which is our approximate temperature distribution that we're going to substitute into this equation. So let's start with t. We know that over our computational domain, temperature is a function of x, y, and theta for our two-dimensional problem. And we're going to write this as W1, which is a function of x, y, times T1, which is a function of theta, plus W2, which is a function of x, y, times T2, which is a function of theta, plus on and on and on to W sub n, which is a function of x, y, and T sub n, which is a function of theta. So we have a bunch of weighting functions, W's, that are spatially dependent, so they depend on x and y, and we have a bunch of temperatures that are only a function of time. And what we're going to find is that each of these temperatures, T1, T2 through Tm, these are going to be the temperatures at nodes. So we'll have a bunch of these, nodes in our finite element mesh. So if this is node I, T sub I, which is only a function of time, would be the temperature at this node right here. And then these weighting functions, which are only a function of position, these are going to indicate the impact of this temperature on the surrounding area. So Wi is going to be non-zero in these elements that surround node I, because node I has some impact on the temperature within this triangle, and this triangle, and this triangle, and this triangle, and this triangle. So just looking ahead, that's what these things mean. So we're going to let W with an underscore be our vector of these weighting functions. So this is just going to have W1, which is a function of x, y, W2, all the way down to W sub n. And T is going to be a vector with all of our nodal temperatures. This will be T1, T2, all the way down to T sub n, like that. So in matrix notation, then, I can write T as what? I guess it would be W transpose multiplied by this T vector, right? So T, which is a function of x and y and theta, is just equal to W transpose, so W1, W2, all the way to W sub n. So this is W, the vector, transposed, multiplied by our row our column T, so T1, T2, T sub n. Okay, so this is T. Yeah, so T is equal to W transpose times T, like that. Alright, so this is how we're writing T, right? We split it up into sort of the spatial dependence and the temporal dependence. And now we're going to take this idea and substitute it back up here into the weak form of our finite element, our weighted residual equation. So we'll substitute it here and here and here, and we'll get at least a little bit closer to actually doing these integrals. Alright, in order to do these integrals, I'm going to need dt d theta. I'm going to need dt dx and dt dy. So t is equal to w transpose times t. This is a function of x and y, and this is a function of time. So if I substitute this back into each of these derivatives, I get that dt d theta is equal to d theta of w transpose times t. Of course, this is not a function of time, so this becomes dt d theta is equal to w transpose times dt d theta. Dt dx is equal to d dx of w transpose times temperature. This is not a function of x, and therefore this becomes dt dx is equal to dw transpose dx times t. And similar, dt dy is equal to dw transpose dy times t. So I'm going to take now this, this, and this, and substitute them into the weak form of our finite element equation, and we get then the integral over the area of F times rho C times d temperature d time, which is this right here. So this is W transpose times dt d theta times d area plus the integral over the area of K, and inside the parentheses I have dt dx and dt dy. So dt dx is so we have df dx times dt dx, which is dw transpose dx times t, plus df dy times dt dy, which is dw transpose dy times t, integrated over the area. And then we have, we'll move to the other side, the integral over the boundary of f times the heat flux normal to the boundary, plus the integral over the area of f times the generation. Alright, so let's think about what this actually looks like. This ends up being a single equation for given one weighting function here, f. This is a single equation that relates all of our temperatures. Right? If we take, for example, just this term right here, this is this is a row vector, n by 1. This is this is a vector n by 1, and this is a column, so 1 by n. So this ends up being one equation, right? We could write this out and see this a little more clearly. You know, the t is not a function of x and y, so we can pull that out of the integral, just like I could pull this t and this t out of these area integrals, right? So I end up here, if I do this, I get the integral over the area of f times rho c times w transpose dA, and then I'm multiplying it by d temperature, d theta. right? And this is this is W1, W2, all the way to W sub n, and this would be d theta of T1, T2, all the way down to T sub n, like that. So if we write this out, this ends up being something like, what would it be? I guess it would be the integral over the area of f times rho c W1 dA multiplied by dt1 d theta. So it would be the first element to this times the first element to that, plus the integral over the area of f times rho c times W2 dA multiplied by dt2 d theta, plus, and then finally we get to the last element, so it would be the integral over the area of W sub n times f times rho c dA times dtn d theta. So this is one equation that involves all these integrals of these weighting functions and then all these derivatives of temperature. So yeah, I mean, if we just sort of go through all these terms in that way, this ends up looking like a really big equation. So the integral over the area of f times rho c W1 dA times dt1 d theta, plus all of these up to the integral over the area f rho c Wn dA and dtn d theta. So that's basically this part of the thing written out, and then we can do the same thing here. We'll take t out, and we'll get plus the integral over the area of, what would this be? This would be k times df dx dw1 dx plus df dy dw1 dy dA, and then that would be multiplying t1, plus we keep going term by term, and at the end we get then the integral over the area of k and df dx dwn dx plus df dy dwn dy dA times t sub n, and then we have these last two terms that just come to the other side. So the integral over the boundary of the heat flux normal to the boundary times f times ds, plus the integral over the area times f times g triple prime dA equals 0. So that's what we have after substituting in our form the unknown temperatures. A bunch of area integrals that we have to do, multiplied by either the derivative or the temperatures, the unknown temperatures, and but we only have one equation, right? We have one equation for all of these different unknowns, and so the last thing we're going to end up having to do is we're going to have n equations, which means that we have to write this not just for one weighting function f, but actually for n different weighting functions, f1, f2, all the way through f sub n. And what Galerkin's method does is it says that f1 is just going to be w1, f2 is going to be w2, f sub n is going to be w sub n. Right? So basically I'm going to take this equation and I'll write it for f1, and then I'll write it for f2. So I'll write it for w, I'll replace f with w1, I'll get an equation. I'll do the same thing, but I'll replace f with w2, I'll get another equation. If I do that n times, I now have n equations and n unknowns. So we'll write that here. Okay, so let's go ahead then and make the substitutions, right? We're going to say W1 is equal to F1, W2 is equal to F2, and so on. So Wn is equal to F sub n, and then we'll write each of these equations for each of these substitutions. And what is that going to look like then? If we start with F1, we're going to have the integral over the area of W1 times rho C times W transpose dA, and this is multiplied by d temperature d time, plus the integral over the area of K. And then if we substitute W1 for F1, we're going to get the W1 dx dW transpose dx plus dW1 dy dW transpose dy dA multiplied by t is equal to the integral over the boundary of W1 times Q normal ds plus the integral over the area of W1 times G triple prime dA. And we would keep writing this, right, for W2, W3, all the way to Wn. So the last one is going to look like the integral over the area of Wn rho C W transpose dA dt d theta plus the integral over the area of K. Now we have dWn dx dW transpose dx plus dWn dy dW transpose dy times dA all multiplied by t is equal to the integral over the boundary of Wn heat flux normal to the boundary ds plus the integral over the area of Wn G triple prime dA. So this now is n equations, right, 1 all the way to n, in my n unknown temperatures. And actually, if you think about what just this part of the system of equations looks like, you'll see that it starts to look like a capacitance matrix times d temperature d time. Okay, so we can write that out. So this ends up being, let's look at what this is. This first part is the integral over the area of W1 rho C W1 dA times dt1 d theta plus, we go to the integral over the area of, let's see, we're still W1 rho C, but now we're Wn dA times dTn d theta, right? And if we went down to the next row, we would be the same thing, but for the weighting function W2, right? So this would be the integral over the area of W2 rho C W1 dA times dt1 d theta plus all the way over to the integral over the area of W2 rho C Wn dA and dTn d theta. And then finally we get to the last one, so we keep going. The last one is the integral over the area of Wn rho C W1 dA dt1 d theta plus the integral over the area of Wn rho C Wn dA dTn d theta. So this is a big n by n matrix of coefficients, or matrix of coefficients that multiply n d temperature d times, right? This is if we want to write this in matrix format, this is going to be something like this. It's going to be the integral over the area of, let's see, what would this be? It would be W times W transpose times rho C dA, and then we are multiplying this by dt d theta, right? Because this is, let's see, this is an n by 1 by 1 by n. This is an n by n matrix of coefficients that looks exactly like this. W1 times W1, W1 times W2, all the way over to W1 times Wn. Right? So this is exactly what we want. This is an n by n array of integrals, and we're multiplying it by an n by 1 column of temperatures derivatives. Right? So let's look at what this looks like a little more carefully. So this is the integral of over the area of rho c times w transpose dA multiplied by dt d theta. So this is w, this is a rho vector like this, and this is w transpose, so this is a rho like this, and if I multiply these two things together, I'm going to get something that looks like this, which is W1, 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 W2, W1, Wn, all the way down to, I guess this would be Wn, W1, Wn, W2, all the way to Wn, Wn. So this ends up being exactly what we want, right? If I multiply each of these by rho times c, and I integrate over the area, I'm going to get a matrix of coefficients that are looking like this. It's the integral over the area of rho c w1 dA all the way to the integral over the area of rho c w1 wn dA. And if I go down, it's the same thing with these guys in the bottom, and then multiplying the whole thing by d theta of all of my temperatures, T1, T sub n. So if we think about what this is, right, look at this again. This is the integral over the area of rho times c times w transpose dA times dt d theta. This is an n by n array of each of these area integrals, and this ends up being basically, not basically, but actually our capacitance matrix. Right? So this is a capacitance matrix times dt d theta. So the capacitance matrix for finite element looks a lot different than it did for finite differences, but actually it ends up being something related to the heat capacity, we'll see eventually. And if I knew what these weighting functions were, I could actually do these integrals and construct my capacitance matrix. So if I write this for all of the terms, what do I have? I have the integral over the area of rho times c times w transpose dA times d temperature d theta plus the integral over the area of k times dw dx times dw transpose dx plus dw dy times dw transpose dy times dA all multiplied by t equals, on the other side I'll have the integral over the boundary of W times the heat flux normal ds plus the integral over the area of W times G triple prime dA. This is starting to look a lot like our finite difference set of equations. This is C, this is an n by n matrix, this is going to be K, this is also an n by n matrix, right? This is this is a column vector n by 1, and here's a row 1 by n, so this ends up being n by n. Same thing here, we're adding them together. This is a vector, so this is what we've been calling Q. This is n by 1, and this is a vector, so this is what we've been calling G. Right? This is n by 1. So this ends up being C times d temperature, d theta, plus K times temperature equals Q plus G. Right, this is very similar to what we have seen before. We're just going to have to construct C and K and Q and G a little bit. So what we need now, and what we'll do next time, is to develop some understanding of what each of these W1, W2, each of these functions actually look like, so that we have some rules for doing the integrations that we need to do to construct C and K and Q and G according to basically this and this and this and this.